So thanks for the introduction. And I would like to start off by thanking Avi for organizing this very nice session. I think this was a nice demand to make a specific session on B-OTDA sensors. This is, as has been mentioned before, it's a sort of a more and more interesting domain of research and applications. And as mentioned Moshe in the first talk, I'm going to address the issue of long-range sensing. And by long-range, normally we target applications which are beyond the 100-kilometer range. And just to say that I'm very happy to have all these all this bunch of co-workers in our lab. And why do we want to go to these huge ranges? And this is because there are monitoring needs in regions that are really unmanned. And by unmanned, I mean situations like the Sahara Desert or Siberia, or really big spaces where there's no person. So you cannot really have repeaters in the middle, and the least systems you have monitoring your facility, the better. And I listed there a few pipelines that I'm aware of would be interested in such technologies. And of course also maybe offshore wind farms. You know that we are pushing these further away because we don't want to see them close to the coast. So any of such situation you're interested in having systems that cover a really long range. Now, this summarizes, this is taken from, of course it's not, let's say, extremely difficult, but this summarizes very well the problem of range in these B-OTDA sensors. This is taken from a paper by Luc here. And you see here the effect of the pump. So you send the pump pulse through one side, you send the probe pulse through the other side. And of course your response, as mentioned before by Luc, scales with this exponential decay. And the exponential decay, I want you to note that it decays with twice the attenuation of regular fibers. So it means that it is twice more challenging because you have two waves interacting. So essentially, just putting this into figures, in terms of signal amplitude, if you increase the resolution by a factor of 10, this is essentially equivalent to raising the range by only 25 kilometers. So putting this very straight, if you reduce your, if you improve your resolution by a factor of 10, you will hit the deadlines. But if you improve your range by a factor of, by just 25 kilometers more, nobody will really care too much. So it's just exactly the same problem in terms of signal amplitude. It's exactly the same problem as you see here. So this is the typical exponential decay where you really see at the far end of the fiber, close to the end, that the signal amplitude becomes really comparable to the background noise that you have in detection. Now, we have another problem that typically scientists like me oversee quite a lot, and this is the fact that in B-OTDA you use two waves. So it means that you have to take your probe wave up to the position where you start your sensing and carry it all the way up there and back. So if you don't want to have any kind of active element all along your facility, and you have your, let's say, 50-kilometer range set up, which is a typical standard for commercial systems, then of course, if you have nothing there in the far end, if you cannot afford to put any kind of system there in the far end of the fiber, your range is limited by really half of the sensing range. So your linear sensing range is limited to half of the nominal range of the instrument. So this you try to shortcut in different ways, but really, if you're crossing unmanned areas, this is a complicated problem. Now, if we plug figures into the previous expressions and we say, well, how much far can we go with a typical configuration? So, as mentioned before, the probe power is limited by SBS threshold. Pump power is limited by modulation instability. If you probe powers, you see that for a 100 kilometer scheme, you will have to measure nanowatt variations with 100 megahertz bandwidth if you want to keep your meter scale resolution. So considering typical noise powers in detection, this is pretty challenging. So you require thousands of averages, and in the end of the day, the measurement is so lengthy that you're not at all interested. So you have different strategies to improve range. Simplest is just to use a preamplifier in detection. This works a little bit, but if you put a preamplifier, you will at some point of gain be dominated by signal ASE or ASE-ST beating, and these noises scale with the square of the gain. So in the end of the day, you're just interested in having as much gain as you're comparable to the shot noise or to the thermal noise. So going beyond that, having more amplitude will just give you also more noise, an increased amount of noise, and in the end, your signal-to-noise ratio is not at all improved. So just is good enough if you go close to the limit of overcoming thermal and shot noise. And with typical settings, you can plug in figures again to this, and you will see that you can afford a few 20, 25 kilometer more with similar performances. Postcoding is another very interesting thing proposed by a group in Italy. So essentially, the whole idea here is if you have a single pulse trace, this is what you would see here at the left. So if you code your traces, means that you put several pulses, a sequence of coded pulses into the fiber, you will get the linear superposition of all those traces in your detection system. And if you have this linear superposition by using simple algebra, you can deconvolve or you can decode your single pulse trace and recover. You can recover the single pulse trace. And the benefit here is that, of course, if you use very long sequences of pulses, you have much more energy to measure. And obviously, this gives you an enhancement of signal-to-noise ratio. This enhancement scales with the square root of the code length, as you see in that expression. And for typical affordable code lengths, because this has also some difficulties in implementation, for affordable code lengths, you might have signal-to-noise ratio enhancements of 10 dB, which again is just 25 kilometers. So we are fighting every 25 kilometers. Every of these things is just having 25 more kilometers. Every 10 dBs that we gain in signal-to-noise ratio is just adding 25 kilometers. And last is just using the sensing fiber as the amplifier itself. So you benefit from a stimulated scattering that arises in the fiber, and you use the sensing fiber as an amplifier itself. So you're transferring power to the pump and probe at every section along the fiber under test, and this breaks a little bit the limitations in the expressions of the double exponential that we saw before, because you're amplifying both things. You're amplifying probe and you're amplifying pump, so it means that your expression for signal variation is no longer what we depicted in the first slide. So the good thing is here your sensing fiber itself is gaining, and it's bidirectional. So it means that you have gain in both pump and probe at the same time. So you can wash out the effect of losses, and to a certain extent, improve your sensing range. Of course, this has some issues, as we'll see now. So for those of you who are not aware of what Raman scattering is, it's just transforming a conventional optical fiber, any type of it, into an amplifier, and a fully distributed amplifier. So you have a 100 kilometer long amplifier. And essentially you achieve this by pumping the fiber with a high power laser at a wavelength that is some 100 nanometers below your signal wave. And this is what happens when you pump through one side. You push your maximum gain, which originally was at the beginning of the fiber. Here you're pushing it some 15 kilometers inside the fiber. If you pump through the other side, you get better far end contrast, and if you pump through both sides, you're having this kind of flat response that sort of even out the effect of losses. But of course you have to pay for this, and the fact that your pump is quite noisy, and this noise is transferred to the probe wave. So you're really paying this as a sort of payload. There are second order schemes that allow you to even out even more the power evolution along the fibers. So this is just having a pump 2 Raman shifts below your B-OTDA signals. With your first Raman pump at 1365, you generate an homogeneous Raman pump along the 100 kilometers at 1455. And this 1455 pump is transferring quite homogeneously power to our B-OTDA signal. So in this way, you can achieve really very flat, as you see that green trace is very, very homogeneous power transfer to the probe wave. And this is just combining all these things wisely, a very nice result that was obtained this year. This is a 240 kilometer sensing loop, so it means that you have 240 kilometers of passive optical fiber, and of which 120 are really measuring. The other 120 is just to take your probe signal 120 kilometers away. And of course, it involves all the technologies that I just talked about. This is preamplification, coding, and Raman amplification in the sensing fiber, and the second order scheme for the pump, and the first order scheme, Raman assistance scheme for the probe. And this is the kind of thing that the kind of trace that you obtain. In this case, there's no exponential decay, as you see. You have your maximum gain is shifted some 30 kilometers inside the fiber. You have a little bit of contrast there in the end, the 120 kilometers. And this is just showing that effectively, yes, you can measure at the end of the 120 kilometers. Now, it's pretty difficult to say that there's going to be possibility of extending these results much, much further. Of course, there is a little bit of possibility, but we are really approaching the limits now. But okay, we are still working on it. So just to finish, I'll say the range limitations really put restrictions in several application scenarios. I've just reviewed a few of the techniques that can be used to overcome these limits, and really what has been proven so far is that the wisest strategy is a combination of all these methods. Yeah, just to show, we have demonstrated this 120 kilometer linear sensing range, and because it was in the title, but I couldn't afford it because of time, we have also demonstrated quite recently a 120 kilometer range vibration measurements, meaning that you have a linear sensing range of 120 kilometers for sensing vibrations, using phase OTDR technology where you don't have this carryover fiber problem. This is still one interesting thing, and of course I'm open for questions now.